We'll now take a look at some common nonlinear equation types. So far, all the equations we've been dealing with in this course are linear. They may have multiple variables, but the key point is that each variable is raised to a power of no greater than 1. There are several common nonlinear equation types, including quadratics, cubics, and higher order functions, exponentials, logarithms, and trigonometric functions like sine, cosine, and tangent. We'll review a few of these today. Let's first take a look at higher order functions. Polynomial functions may come in any order, from 0 to infinity. The order of a function is the highest exponent to which the function is raised. A quadratic or parabolic function has an order of 2. A cubic function has an order of 3. The number of solutions to an equation is equal to the order. So take, for example, the equation x squared is equal to 1. The order here is 2, which means that there are 2 solutions. And indeed, if you think about it, you can see that the solutions to x squared equals 1 are 1 and negative 1. Both of these values squared equal 1. Look for a moment at the graph of the parabola, or quadratic function shown. The function shown is y equals x squared. You can see from the function that there are 2 solutions for every value of y in this equation. When y is equal to 1, for example, x equals 1 or negative 1. When y is equal to 4, x is equal to 2 or negative 2. Only at the vertex, when y is equal to 0, is there one solution, because there's only one square root of 0, and that is 0. Let's look at a couple attributes of the quadratic function. Again, we can see that the vertex is centered at 0 for the standard quadratic, and there's an axis of symmetry extending from the vertex straight up. By an axis of symmetry, we mean that the function is a mirror image of itself on each side of this axis. This makes sense because the 2 solutions to the quadratic function are going to be the positive and negative value of x, which squared equal y. We can shift the vertex around. For example, if we add a constant to the function x squared, then the vertex is shifted in upward direction by the value of the constant. So x squared plus a has a vertex at x equal to 0, y equal to a. If we add parenthesis around the x and subtract or add a constant to the x within the parenthesis, we can also shift the parabola in a horizontal direction. We can see that if we subtract b, for example, we will add b to the x value of the vertex. Now let's take a look at exponential functions. Exponential functions are written very simply in the form a raised to the power of x, where a is any constant value. If we take a look at these 2 graphs, we see some common attributes. First, the y-intercept of the graph, or the point at which x is equal to 0, the function's value y is always equal to 1, no matter what the base, or the constant, a, is for a given function. However, we can also see that the steepness of the function differs. If a is greater, the function is steeper, because the exponential increases more quickly. Similarly, as a decreases, you get a much wider function, but in each case there's an increase. However, when the value of a drops below 0, x drops below 0, the value of the function is always decreasing, growing closer and closer to 0. As we discussed, the vertex of the function is always at y is equal to 1. However, if you add a constant to the function so that you have a function a raised to the power of x plus a constant, then the y-intercept of the function will now be 1 plus the value of the constant. The inverse of an exponential function is a logarithm. An exponential function is essentially the same as a logarithm, except the x and the y value in the function are switched. There's an axis of symmetry between an exponential and a logarithm with the same base value along the line y equals x. In nature, there's a special value of the base called e, which is a value of approximately 2.72. This value is found in nature very frequently, such as in equations for cell growth, and it has a corresponding special logarithm called the natural log, which is denoted ln. Finally, we'll take a look at some sine and cosine functions. Sine and cosine functions are special functions compared to the others we looked at because they're trigonometric. They're not algebraic. So the function sine or cosine is simply written sine x or cosine x. Sine and cosine are periodic functions. Essentially, they're squiggly lines that repeat, oscillating from positive to negative. The standard sine and cosine have a height of 1 at the greatest height above 0 and -1 in the trough below 0. However, this height can be changed by multiplying the function sine x by some constant a. So the value of the amplitude for a sine x is equal to a. 2 sine x would have an amplitude of 2, or a maximum value of 2 and minimum value of -2. The width of the cycle from positive to negative and back to 0 again is determined by the period. This is a constant p that's multiplied by the x within the sine function. So sine p of x has a period of p times 360. The standard period is 1, so the period is 360. However, if p is equal to 2, the period would be 720, so the period of the function would be slower. And if p is decreased, the period of the function would be faster. So it would go from 0 to positive to negative and back to 0 much more quickly. Let's look at what the sine and cosine function really represent. The function represented by sine x is shown here. As we discussed, it's a periodic or repeating shape. The x value represents the point on the unit circle in degrees or radians, and the y value represents the y value of the unit circle centered at 0 for a given x value. What does this mean? Let's take a look at our unit circle. 0 degrees occurs on the unit circle at -1, x equal to -1, y equal to 0. So at this point, the value of y is equal to 0. And you can see at 0 degrees on the sine x function, the value of y is equal to 0. Now move 90 degrees in a clockwise direction on the unit circle. You're now at a value of 90 degrees, and the y value is 1. So on the sine x function, the value of y at 90 degrees x is equal to 1. Move clockwise around this circle again to 180 degrees. Can you see the correspondence between the sine wave and the circle? We see that 180 degrees, the value of y on the unit circle in the Cartesian coordinate plane is 0. And indeed, on the sine wave, the value of y is 0 again. We move another 90 degrees, we're at a total of 270 degrees, and the y value is -1. Same on the sine wave. And finally, when we move another 90 degrees, we're back to our circle, 0 point. So we've gotten a whole period from 0 to positive to 0 to negative and back to 0. From here, the function simply repeats. Consider the difference between the sine and the cosine wave. The cosine wave works just in the same way as the sine wave does, but the 0 degree point is shifted by 90 degrees in the clockwise direction. So in this case, the value of 0 degrees is 1, and the function begins at +1, falls to 0, goes to -1, and returns to 0. Take a look momentarily at the cosine wave. Do you see the correspondence between the degree values and the y values on this unit circle and the degree values and y values on the cosine wave? In summary, there are many different types of functions. We could go on all day about different kinds of functions, but most are available in reference books. It's important to be able to look up functions, understand their properties, and interpret graphs of the functions. And the key skills associated with this are being able to solve for functions using balancing equations,